So this video will be about the bearing sizing, and some videos you should have watched are the basic explanation of what the powertrain is, and you should recognize exactly how the powertrain works using where you have the motor and you have your sprocket, and then your chain acts, your chain, another sprocket, your diff, and how power gets transmitted. You should be familiar with that. And then this one will be specifically talking about how we calculated or validated our bearing sizing. So first of all, we have to calculate the chain tension. So our chain is going to apply a load such that basically, if I take a picture of our current powertrain, when the system is spinning, the chain is going to pull in like this on the sprocket, and we have to calculate what this load is. And the way we do that is you can either, if you have the sprocket, right, you have, let's say this 11 tooth sprocket, this sprocket will have a certain radius. I believe it's 2.2 inches, right? That's the diameter. So the radius is about 1.1 inches. And we know the peak torque that can go through here. That's specified by the motor, and that's 150 Newton meters, right? And so from there, you could calculate the force because we know that force times radius is going to equal torque. Therefore, if we want to find the force, we could take the torque divided by the radius, and we could get the force that's expected to go through it. This has some approximations with it because we would be assuming that the entire force would basically be applied only in like one direction, like this, which is not the case. Load is also applied over here on the slack side, but it's a good enough approximation. The other way we can do it is we can look at the power being transmitted and the velocity that it's going at, and then from there we could calculate the force, and that's the way we've done it. So these are the four equations we use in order to calculate the chain load or chain tension. That's what we call it. And then we figured out what and this is. And so these equations tell us that for our system, we expect a load of 1,200 pounds, roughly. And so from there, we have to calculate the load that's on the bearings because this 1,200 pounds isn't actually going into this bearing or this bearing. Instead, what's happening is we can treat this like a beam, right? If we have this is our differential. This is our this is our first bearing. So there's a support over here, second bearing, support over here, and then this is our force. So the force over here. And then we'd solve for the force acting on this bearing and acting on this bearing. And that's what we've done over here. And we've solved that, and we get that there's a 1,500 pounds on this bearing and 300 pounds on this bearing. And then we have to actually size the bearing using those values, right? So we use SKF. So when we go on SKF's website, they have this thing called Product Select where you can put a lot of filters in and choose the appropriate bearing. So this has to go on the differential, and the differential is something we buy, it's not something we make. And so it's the bore diameter that you need is set basically by Drexler. So on this right side over here, we have that the radius is 27.5 millimeters, which means a diameter of 55 millimeters. It can't be anything less or more, and we can't control that, so we just say put a filter 55 millimeters. Next, we talk about bearing type, and we use deep groove ball bearings because they're very good at handling radial load. And what radial load is if I clear some space over here. Radial load is essentially if you had this, then radial load would be stuff acting on here or acting on there. Meanwhile, if you had a load going into the page or out of the page, that would be considered axial loads. So in this application over there, in this bearing over here, the radial loads would be like this, and axial loads would be like this. They're very good at handling heavy radial loads, which is what we experience. I mean, this experience is 1,500 pounds, so a lot of radial load. But we still experience axial load because when we're cornering, for example, the differential will want to move and the bearing is stopping it. This is not that much of a load, but we can't simply use like needle bearings because it is expected to experience some radial loads, especially like shocks and on bumps. So that's why we use deep groove ball bearings, and they're very easy to get and also, put into our system. That's why I use deep groove ball bearings, single row, and then we use capped ball bearings because, I mean, think about the environment that this is in. This is inside of a racing car, and that racing car, the bottom it's kind of exposed to the environments. Like we do have the um, what's it called? Like the arrow thing at the bottom, which helps prevent. I'm blinking. I forgot what it's called. Yeah, I don't remember. But you have like an arrow thing at the bottom which helps protect against some of the grime. But I mean, the environment is not the epitome of cleanliness. This isn't the lab environment. So we don't want any grime buildup inside of our bearings because replacing our bearings is a very big pain. And if like sometimes, like for this bearing, we might be required to remake the entire output shaft just to get that bearing in. So it's not realistic to be like, oh, hey, just get something that's not sealed and just replace it later. For us, making it sealed makes the most sense. And then you have the basic load ratings. We're going to keep this empty for now, but I just want you guys to see the roller bearings. So, I mean, after those filters, we don't have that many options. And so I mean, all of them have the same bore, but as you can see, some are larger and smaller, and this will affect these load ratings. So this C stands for dynamic load rating, and the CO stands for static load rating. So static load rating is if the bearing is rotating very, very slowly or stationary, that's the maximum amount of load it can handle without it permanently deforming. And a dynamic load rating is if you were to subject this bearing, for example, 61811 to RS1, to 7.15 kilonewtons while it's spinning, so not very slowly, but like actually doing stuff, then you can expect this bearing to last 1 million revolutions if you were to do exactly 7.15 kilonewtons. This without taking into account some factors, but in general, if you were to put 7.15 kilonewtons while it's spinning, you could expect 1 million revolutions, which isn't actually a lot for a bearing. And so this is the number we care more about because our entire drivetrain is always like moving faster than at least 100 RPM. You're never going to go much slower than that. So you can effectively ignore CO. I mean, keep it in the back of your minds, especially when we talk about the output shaft. But for now, just consider C. And so how do we know what C rating we want, right? So do we want something that's 74.1 or do we want something that's 29.6, right? Like how you know what type of a C rating do you want? And so we have a calculator for that. It's called this bearing life calculator. And so what it does is it uses L10 formula. This is basically the life expectancy of bearings. And so the way this is done or is through a lot of empirical testing by like manufacturers and professionals, and they found out that 90% of bearings in a large enough sample size are going to meet this criteria. So if you solve this equation and you get that the expected revolutions is 1 million revolutions for your bearing, then if you were to do 10 bearings, 9 out of 10 of them would be expected to do at least a million revolutions, and one would fail due to fatigue reasons. But overall, we can just treat this as it is. And so what I've done is I've specified the amount of miles we expect the car to run. I put a factor of safety. I specify the tire radius and the gear ratio, and this will tell us the amount of revolutions that are required by the diff and the motor in order to accomplish this thing. This life equation exponent, that's just a static number. It's this P over here. It's 3.33, I believe, for roller bearings, but for ball bearings, it's simply 3. We don't need to worry about that. And then this max force is basically what's the maximum amount of load that's going to be expected on this bearing. And so 1500 is the load, put into this 6.677, put it into here, and this at max power. You don't really need to worry about that. And then this cubic mean torque, what that is we have data. So we did drive days in Michigan, and that told us like over here um, what the like us RPMs, power usage, torque usage versus time based on our driver. And it's probably this is some of the best data that we have because we don't have too much data. So when we did this drive day, we uh, we power limited it, but it probably matches what endurance is. And what power limiting is we can run a maximum of 80 kilowatts. So at one point in time, we can only push 80 kilowatts, but we power limit. So you say, oh, hey, you can't exceed 30 kilowatts of power. You can't exceed 20 kilowatts of power because during endurance, which is like around 28 minutes or 22 miles, our car, we don't have the capacity to be able to run at 80 kilowatts for 30 minutes. So instead, we power limited it to like 20 kilowatts so that you are able to actually, finish the entire endurance. And so we were power limiting it at this time. It wasn't to the point of endurance, but I mean, we're trying to be conservative here. So we use these values. I exported it as a CSV, and then I inputted all that data into this Google Sheet, and I calculate for the cubic mean torque. And what this cubic mean torque is it's basically it's not the average. Instead you basically take the average, you cube the average, and then take the cubic root of that. And this is advantageous because when you have data, you're going to have like peaks and valleys. So if I were to go back here, you can see it's very spiky, I would like to say. Like it goes up and it goes straight down, and it goes up straight down. And we care a lot about these peaks because these peaks are not proportional to this, for example. So if you were to double your commanded torque, for example, you're not simply going to double the wear on your parts, you're going to like 8 times it. So we care a lot more about what happens at these peaks than what happens below here. So this cubic mean basically allows us to take into consideration a lot more of these peaks. If you're doing like heat gen calculations, you'd use the root mean square. For fatigue life, we use cubic mean. Why is that? I'm not entirely sure. It's just convention. So I calculated the cubic mean torque, and from here I calculated the cubic mean force. It was, as I was saying, you could take the torque and divide it by the radius, and you'll get your force. Um, I could use the formula, except the formulas that I gave kind of break down when you're not at your maximum power, and they're not really reliable. So instead, I just used the cubic mean force, and that goes into um, yeah, that goes into here. And so this is the cubic mean torque, and this cubic force is basically the amount of load that is expected to act on the, what is it called? On your bearing based on that load. And so we can calculate the dynamic load by setting this L10 life to be at the certain revolutions that we require, solving, take dividing or taking the cubic root and then multiplying it by P, and you solve for C. And so we give it a dynamic load rating of 2.86 kilowatts. And now if I go back to product select, the minimum C that you're seeing is 7.15, which clears the requirements of 2.8, right? We use 61911 RS1s, and as you can see, these are pretty bulky compared to what we need. They use 16.5, right? And so when I put them into the calculator of a dynamic load rating, and I go like 16.5 over here, like you can see that our factor of safety, even at max power, assuming that every single revolution happened at max power, you have factor of safety of 50 on top of this. So it's kind of absurd. Um, we maybe in the future we can look into using 61811s instead of 61911s. But for right now, we have plenty of 61911s, and our current priorities aren't in trying to minimize the weight. It's trying to have a reliable car. And so if in the future we find that we can go down to 618 ones, then we should, because the numbers clearly are in its favor. But yeah, and then yeah, two RS1s versus two RZs. If you're like, why do you use the RS1s instead of the RZ? I believe these are non-contact seals and these are contact seals, so you can get to higher revolutions with those. But if we go to this data sheet over here, it goes on the differential, so it only needs to spin at a maximum of, I believe, 1,500 RPM or a little bit less. And so as you can see, limiting speed 5,000 RPM, plenty. So we don't need to worry about the rotating speeds. So we use the RS1 for the better sealing. But yeah, that's how we size the bearing over here. And then this left bearing is the same story. I'm going to go to SKF Product Select. This is 50 millimeters instead of 55. And then the load that's on here is only 301 pounds, right? So 301, 1.339. So I put this into here. And then I have the dynamic load rating. Minimum is zero point 0.3. I go into the SKF Product Select. I'll filter by C ratings. And so the smallest bearings we could use is 6.181, which easily clears any requirements. And so if we go into the CAD, if we were to see what bearing we're using, I can't remember, sorry, 6.810 to RF1. So it is in the requirements. And if I were to put the 5.4 into here, 5.4, you can see like factor of safety is insane. 216, 4,000. So the smallest bearing in here is easily fine. Maybe in the future we could use 6.81s, but I digress. And then we go to the output shaft. the output shaft is a lot harder to actually size than the differential. And the reason for it is because it's statically indeterminate. So if you were to look, this is our output shaft that we manufacture, this aluminum piece over here. It connects to your sprocket and it connects to your bearing over here. This bolts into your motor. So if I were to go here, you can see it bolts into your motor, and this connects to this ring over here, and basically this is your second output shaft. So if I were to go over here, right, you have a bearing, bearing, and so basically what I circled over here is the internal output shaft, and then your external output shaft. And so if you look, there's one bearing, two bearings, three bearings. So I don't put the distances here, but one, two, three. You can try solving it, but this is a statically indeterminate problem because there's three supports instead of two. So there are hand calculations you could do to solve for the force that's on this third support, but it's very, very tedious, and it makes a couple of approximations. So instead, we use SKF SimPro Quick. This is basically SKF's quick modeling software that we can put in our bearings, we can put in speeds, we can put in forces, we can put in bearings, and it will calculate the amount of load that's applied on the bearings, right? And this is very nice for us. And the way I've done this is I've created a mock output shaft. This is my motor shaft approximation. So this is the internal output shaft up to about the middle point of here, and then you have your external output shaft. And I've exported this as a step file and imported into here, and then put the bearings in the correct locations. I ran the sim, and then I'm just gonna cancel this because I already ran the sim, and this tells me the amount of load. So you can ignore the rating life over here because it's very, very conservative. Um, but maybe did I change the load? Let's see, 2,300 I did. So I was just messing around with stuff, but if we go to here, this load is 1,200. I mean, yeah, this load on the side is still 1,200. I don't know why I said 1,201. And then 1,200, okay, call it a day, and then report it. I want to save it. Yep, ignore the errors. I don't know how to deal with them, so I can maybe figure that out later. But for our intents and purposes, it's fine. And so we get that the force that is on the bearing is 7,234 newtons right there. And if you want to see the deflection, then here's the deflection. I believe they have an animation as well. So animate this. Yeah. It's scaled a lot, so this is an exaggeration. That's how the output shaft is moving. So if I were to change the deformation scale to be like just 10x, you can see it's very minute. And if I just go to default, just the one, yeah, you practically can't see the deflection. And so this tells me that the force acting on this bearing is 7,234 newtons. And we verify that using SolidWorks. So if I go over here and I go to the static simulation, what I've done is I've inputted a bearing supports, basically where the three bearings are, and I've approximated them as fully rigid objects. And what I get is that if I can go here and I list the connector forces, this is bearing, what, sorry, SolidWorks is lagging. I love SolidWorks, give me a second. Okay, maybe I took a picture of this. Hopefully I took a picture of this because I have no idea what is happening with SolidWorks. Yeah, okay. Let's see, do I have a picture? Please not a picture. Right there. So 6,000 newtons. So this is less than the 7.23 kilonewtons as specified by the SKF software. But this was when I approximated the bearings as being springs. So I didn't make them infinitely rigid. And then, well, I don't know why the result isn't really showing up. But then when I approximated them as fully rigid objects, I got that the force was around 8 kilonewtons, which exceeds what SKF is telling me. And so that means that I can trust SKF's answer because the stiffness that I put that got me 6 kilonewtons was clearly less than the actual stiffness of the bearings. And the load that SKF is telling me is less than fully rigid bearings, which matches like intuition and reality. So we can trust SKF's numbers. So now we have the actual load of 7.234 kilonewtons. And I mean, this seems easy, but like the first time that I was doing this, I probably spent like 4 hours because I was losing my mind. But now that we have set it up, it's pretty fast. And so now if I go to this bearing life calculator, I go to motor bearing calc and I put the 7.234 kilonewtons, right? Oh, we can get that we need a required dynamic load rating of 2.86 kilonewtons. So I'm going to go to SKF Product Select. And now I'm not going to solve for bore diameter. I'm going to say I believe it's let me go here. So this is the idealization of our splines, and you can see it's what is the diameter? 25 millimeters. It doesn't make sense for the output shaft here to be less than 25 millimeters. So I'm going to set the minimum bore diameter to be 25 millimeters, and let's go up to like 35, right? And then the same filters on the left side. And then again, I'm going to sort, or it's already sorted by C ratings. And so we know that we need a seed rating of at least like at minimum of 2.8. Um, Okay, I think we are good. So we know from the calculator that we have a required dynamic load rating of at least 2.86. So I'll be setting a filter such that we'll only look at bearings above 3.3 kilonewtons. So I go to here. Let's go 3 to like 15, I guess. And so we have the bearings. And so, as you can see over here, 3.38, this will technically work. And we use bearings over here. We use 61906, 2RS1s. And so you might be wondering, like, why don't we use this bearing over here? It's smaller, it has a dynamic load rating that works. And the reason is that this static load rating is very, very low. We have a load of what, 7 kilonewtons? Yeah, 7 kilonewtons, and the static load rating is 2.5 kilonewtons. And so I'm worried, like, even though we're not in the static application, what I'm concerned about is you're going to have permanent deformation even at when you're rotating. And like this is double the dynamic load rating. So for me, it's not worth the risk to go such a low bearing and put it on our car and then fail because of this. So instead, we use the 61906 because their dynamic load rating is a little bit higher than the like expected load. So if you were to go here, this expected load is 7.234 and the load rating is 7.28, which is slightly higher, which I don't want to go any higher than the dynamic load rating. And then if you go over here, like that's the first one that does it. And we use 2RS1s again because, better seal. But yeah, that's the main reason. Maybe in the future, if we get like a dyno working, we could try using like a 61805s and seeing, oh, hey, does it run? Is there permanent deformation? Is there damage? Are we good? Right? But right now, there's no point in risking an endurance run or an endurance finish to save a little bit of weight or to like, have a slightly smaller profile. So that's why I use the 61906s. Oh, oops, clicked the wrong thing. And on this, and you see for factor safety max power, you can see that it's less than the actual expected amount of miles that it needs to run, right? And you might think this is a concern, and it's really not because 80 kilowatts is something we would run during acceleration and during skid pad. And even then, you wouldn't hit 80 kilowatts entirely. You'd probably be hovering around like 60 or 70. And so this 80 kilowatt limit is like the absolute like worst case, and you're more likely to expect something like this cubic mean torque or power, and so this 16 factor safety is fine. And then something I didn't explain is what is this this four factor safety, right? There's no new load case, and it's basically based on this chart reliability. So I said over here, this is the L10 life. So 90% of your bearings can be expected to succeed, and then 10% would not. And so if you want to get higher reliability, like 99% for example, then you need to put a correcting coefficient onto this equation of 0.25. So that's what I've done. I've basically taken this, or basically done this calculation again, except I've multiplied it by 0.25 instead, which is this, and then same over here. And so you can see we're good even with the 99% reliability, which is all we can really ask for. And same over here, which is kind of absurd. But yeah, that's how we size our bearings. And then yeah, we don't normally re-grease or like lubricate our bearings because they're sealed and they're kind of inaccessible. So we don't. We could look into doing that. And we don't use a grease or some type of a paste in between the bearing interface and where it's going in. But that's separate.